Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Douglas Natelson, who is Professor and Chair of Physics and Astronomy at Rice University. His research group focuses on the electronic, magnetic, and optical properties of nanoscale structures. Welcome, Doug.
Thank you. Happy to be here.
Yeah, thanks for doing this. So I want to start with your commentary in Physics Today a couple of years ago, condensed matter's image problem. You say condensed matter is the largest discipline within physics. It has enormous influence on the average person's daily life. Nonetheless, the field flies under the popular radar, routinely upstaged in the press, television, and popular literature by news of astrophysical exotica and the quest for new elementary particles. I agree with you, Doug. I used to have an engineering background, and when I think about physics, I generally just think about the astrophysical exotica that you mentioned and the particle zoo. So what exactly is? Let's go to the basics. What exactly is condensed matter physics?
So condensed matter physics is what is the modern name for what people used to call solid state physics, but I think people wanted to include liquids as well. So that's why it's sort of condensed phases, distinct from gases. And the whole point of condensed matter physics, the whole philosophy behind condensed matter physics, to use the word in a non-professional way, is that there are emergent properties that happen when you bring together large numbers of constituents that maybe interact via very simple rules. You can end up with emergent behaviors and emergent properties that are not at all obvious.
Yeah.
So the example I mentioned in the commentary and that I've talked about in other places is water molecules, right? So a single water molecule is a fairly easy thing to picture. You got your oxygen atom, you got a couple of hydrogen atoms hanging off there. They're sharing electrons. You can almost picture this whole thing as sort of three balls connected by springs. It's got vibrational modes. It can rotate. And it's small enough that you could actually imagine solving the Schrodinger equation and trying to understand its electronic properties, its energy levels, all of that. But the fact is, understanding the properties of a single water molecule does not tell you anything, at least nothing obvious, about wetness or about the fact that snowflakes have six-fold rotational symmetry. And so somehow one water molecule is not wet. One water molecule is neither a vapor nor a liquid nor a solid. But when you get a few 100,000 water molecules together, suddenly you can have, if the temperature is sufficiently low and the density is sufficiently high, you can form a kind of a six-fold symmetric solid crystal that has very specific rotational and translational symmetry properties. It has vibrational properties that kind of emerge only when you bring these things together. It'll have optical properties that are different from the properties of a single molecule. So condensed matter physics is really the study of trying to understand and catalog, in some sense, all the emergent states that happen when you bring atoms together, and their properties. And this can include electronic properties, optical properties, mechanical properties, magnetic properties.
And so would you say in that sense, Doug, it's closer to engineering and material sciences?
Well, it's certainly close to material science, except that, again, I have a sort of a particular point of view on this. The way I figure it is, when I talk to students and try and explain the difference between science and engineering, obviously there's a continuum, right? There's no hard and fast boundary between science and engineering. But in general, physics in particular is concerned with trying to understand the rules. What are the organizing principles? What are the rules that govern how matter behaves? And then engineering is, okay, we understand the rules, and now we have a particular problem of utility that we're trying to solve. So let's do something clever and leverage the understanding of the rules that we have to solve our problem.
Yeah.
So these are related things, but they're not the same.
Right. But there's a solid state physics, as you mentioned, as it used to be called. There are so many applications of it, right? I mean, in everything that we do today, we are feeling it. And so in that sense, it is really applied physics, is it?
It doesn't have to be applied. I mean, I think it can be applied. Certainly many aspects of condensed matter physics, and even atomic, molecular, and optical physics are now applied and have been useful for technologies that we use every day. But I think there are just some really interesting and fundamental properties that we learn about that come about in these contexts. I mean, what's particularly interesting to me is that these days there's actually a lot of crosstalk between the condensed matter world and the high energy physics world, right? So somehow, I guess, here's what I would say: there's this tradition that goes back, I suppose, a bit over 100 years of reductionism, where people have this idea that, okay, if you want to understand matter, you have to understand the particles and fields out of which matter is built. And that eventually leads you to particle physics and trying to understand the ultimate tiniest constituents of matter. And I think that's the reductionist approach, right? Yeah. And the emergence approach, which is a complement to that, says, well, knowing the mass of the Higgs boson tells me nothing about why diamond is transparent and an extremely good thermal conductor and the hardest material out there, right? And the point is that there are, in the same way that there are organizing principles in high energy physics that people like to talk about symmetry and about special quantum numbers that are preserved. Condensed matter physics has exactly the same underlying rules, and there are kind of beautiful emergent things that come out in condensed matter that frankly there's ideas that originated in the high energy community that appear not to exist for fundamental particles, but absolutely exist in the condensed matter context. So, one example of something like this, when Dirac was worrying about the Dirac equation back in the day, and you could write down an equation for how the energy of massless fermions. So if there's two different, there's different statistics of particles. There's fermions are these objects that have spin 1/2 like electrons, right? Yeah. Dirac had this prediction for there were a bunch of predictions for, because the math was relatively straightforward, for how massless fermions should behave. And it turns out that there appear not to be any massless fermions. I mean, even neutrinos, which are very, very light and are fermions, do not appear to have no mass. But in graphene, for example. Graphene is a monolayer of carbon atoms from graphite. So if graphite is a very layered material, if you peel off one layer, that's graphene. The way electrons move in graphene, they move like, in the sense that their energy and their momentum are related in the same way that Dirac was talking about for these massless fermions. So it's a really remarkable thing, right? Like, electrons are not massless objects, and they have a mass of 9 times 10 to the minus 31 kilograms. And if you have an electron just off by itself floating in the room, if you push on it, it will accelerate as if it's got the usual relationship with energy and momentum for a free particle. But if you look at the electrons that are in this layer of carbon atoms, and you look at basically the electrons that come from the p orbitals of the carbon atoms, they move like massless Dirac fermions. And why do they do that? Well, it's because of the particular symmetry of the material and the arrangement of atoms and exactly how many electrons you have in there, that you end up with these emergent properties. So there's a lot of stuff in condensed matter that is, these ideas of symmetry and these ideas of quantities that are conserved, they're conserved when the electrons, say, are inside the solid, but if you took away the solid, they wouldn't be conserved anymore. All the ideas, all the deep ideas that show up in high energy physics show up in condensed matter as well, is what I'm trying to say.
Yeah, it sounds like a very exciting discipline, as you say, sort of in some sense similar to high energy physics. But here you can run some experiments without spending tens of billions of dollars, I would imagine.
That was certainly something that appealed to me when I was a student. I kind of liked the idea that I could have all of the tools I needed to do interesting experiments, and they would in fact fit in one room. And the number of authors on the paper might be 3 instead of requiring a $20 billion facility with 1,000 collaborators just to keep it running. So it's different in that respect. But I think condensed matter, there's what I wish people had, what I wish the popular public had, was an appreciation of just how amazing the physics of the everyday world around you is. The physics of the everyday materials around you is amazing. Now, I know it doesn't sound terribly exotic to say, see, in condensed matter, we can explain why copper is shiny, or we can explain why you're not falling through your chair right now, right? Or why you don't fall through the floor when you stand on the floor. But the reasons behind those things are actually quite remarkable and fascinating. I mean, the reason you do not fall through the floor is the same reason white dwarf stars don't collapse. Okay. It's all because of the Pauli exclusion principle. The quantum mechanical nature of electrons says that it costs energy to cram more electrons into a smaller volume, costs energy, and this energy has nothing to do with the fact that they have charges and that they repel each other. This is not the Coulomb repulsion. There is just energy associated with having fermions confined into a small volume. And that is really the reason why solid matter can't pass through itself, even though it's mostly empty space. And it's you can take those numbers and estimate like why materials are as strong as they are, and you get about the right answers. I just wish people didn't. I feel like condensed matter is so ubiquitous. We're so used to some of the properties that we see that we don't stop to think about how amazing it is.
Yeah, as you mentioned, Doug, it is also about sort of the emergent properties of matter at all scales, I would think. I remember, Doug, in the late 80s, when I was in engineering school, my advisor telling me that if you want to make a difference, go look at material sciences, because he felt that is the domain where you could, if you really understand it, you could make some interesting things. And we're going to talk a bit about superconductivity and other things later.
Mm-hmm.
But that is sort of an attraction to this field too, I would think.
Yes. And I think one aspect that I hope people appreciate, you can tell whenever you read breathless press releases from the semiconductor manufacturing community. With certain materials, there's always a bunch of caveats, but with certain materials, we are extraordinarily adept now at controlling their properties on very small scales with almost atomic precision. And that gives you tremendous control. That allows you to achieve remarkable properties that, so-called naturally occurring materials don't necessarily have, right? And so that is some of the attraction of is this idea that really understand how the building blocks go together and how and the interplay between them. If you can, make the equivalent of atomic Legos and you can just put together anything that you want, you could really do some impressive things and solve some impressive technical problems.
So are we getting closer to that, Doug? If we have a specification for a material that doesn't exist today, can we custom create that?
So the phrase materials by design is something that occurs cyclically in the kind of the research community, right? This comes up every 25 years or so. There's a big push that says we should work on materials by design. And I have to say we are closer to that now than we ever have been. This comes, there's a number of different aspects to this, right? So first of all, overarching all of this, you are still governed by the actual rules of chemistry and physics. So you can't arbitrarily make anything, because what you will find is that certain structures are just energetically and entropically more favored. And so, the history of materials physics, for example, is replete with predictions of, if you could make the following compound, it would superconduct at room temperature, or it would have these amazing properties. And it just turns out that you can't make the atoms stick together that way. Okay. And there are some properties that are just because of physics, they tend to be incompatible with each other. So it's very hard to have something be an incredibly good electrical conductor up to high frequencies and yet be transparent, be optically transparent, right? There's always compromises. So because the physics that gives you the really good electrical conductivity is also the same physics that tells you about how charge moves when light hits something. So you can't arbitrarily tune things. But I will say that we're a lot closer than we used to be in terms of being able to manipulate materials. There are diagnostic tools for figuring out what you actually have that are far better than they were 10, 15, 20 years ago. I think there's a paper that came out in Nature like yesterday from some folks at Cornell doing very, very advanced electron microscopy, where they can essentially figure out the positions of all the atoms in a very thin slice of some material. And that's amazing. And the other thing I will say, a very important component of this that is still a work in progress, is the theory side. So you'd love to have real complete predictive power. And the fact is that while we have a number of techniques, a number of theoretical techniques that can do a pretty good job under a very broad variety of circumstances, there are still certain classes and types of materials where it is very hard to compute their properties purely theoretically ab initio. Fundamentally, it's computationally incredibly difficult to truly solve the quantum mechanics problem of many electrons.
Yeah.
And so we can make various approximations, right? And so there are some systems that we're pretty good at now. I think there are techniques for, if you want to understand pretty much the electronic structure and the energy level structure of most simple semiconductors, and you can do a pretty darn good job, right? Or if you want to understand the energy levels and properties of small molecules, we can do a pretty good job. But if you really, there's classes of materials and classes of molecules where it can just be very difficult to get a reliable answer computationally.
Yeah, I was just wondering, Doug, as we were talking. So if we visualize some sort of a multi-feature design universe, physics and chemistry will forbid certain zones in that design space, right? That's one issue that you mentioned. Is that true?
Yes, I think that's true. I mean, this is why, I mean, again, I'm kind of a nanotechnology person, right? I'm a nanoscale. A big component of my research program is work at the nanoscale. And I love science fiction, and I love the science fiction depiction of nanotechnology. But the fact is that you cannot arbitrarily build any structure you want out of atoms by just placing them where you want them to be. I mean, in the end, there are energetic considerations and other considerations that really do limit what you can do.
And geometry won't allow you to get around it?
I mean, I always hesitate to say, I always hesitate to make absolutist statements, but I think, there are certain things that I just don't think you can do. And you can run into the problem that you might be able to make something, but it's not necessarily really stable, right? So it's sort of the equivalent of, I can stack up a bunch of playing cards in a very elaborate structure, but if I, touch this thing at all, it's all going to collapse, right?
Right.
So, there's a reason why, and it's sort of very interesting why we get the structures we do. But if you look at carbon atoms, there's a very limited number of ways carbon atoms like to arrange themselves if left to their own devices, right? You get graphite, you get diamond, you get fullerenes, which are in some sense related to graphite, right? I mean, you're taking sp2 bonded carbon and you're twisting it around in different ways. And then, of course, you can have really amorphous carbon, but that's about it. I mean, so you're not going to get, there's no chemically stable way to make hexagonally close packed carbon. It just doesn't want to do that.
So you also mentioned the theory side. The computational aspects of this is also somewhat limiting. Just because, given the current resources in computing, I would imagine. But if you're successful in quantum computing and we really bump up, these boundaries of computing by many orders of magnitude.
Right. So you've hit upon exactly, this is an attractive potential application, even with the, so-called noisy intermediate scale quantum structures people can make now. There is a clear interest in trying to solve certain kind of electronic properties of molecules problems, right? So yes, I mean that is a real possibility. Is that I guess what I would say is the reason the many electron problem is complicated computationally, and why its complexity grows exponentially with the number of electrons. That's closely related to the reason why the capabilities, if you had general purpose quantum computers, the capabilities of these quantum computers grows exponentially in the number of qubits. So there's definitely interest in if you could make general purpose quantum computers, you could solve certain material problems much more efficiently.
Yeah, I was reading or talking to somebody. I think we are up to 40 qubits or so, but if you can get to 200, as you say, it sort of exponentially goes up. But 200, we have something that would open up so many forbidden areas currently.
Yeah, I mean, it's a very interesting question. I mean, certainly Google's Sycamore machine is 53 superconducting qubits with certain levels of properties. IonQ has trapped ions and can do on the order of 40 qubits, where the fidelity of those qubits, the ability of those qubits to remain in a really kind of in a nice quantum configuration is quite a bit better than the superconducting case. And I haven't read the paper, but I've heard a report that somebody in China has gotten up to kind of 60 superconducting qubits. None of these technologies are quite ready for prime time yet.
Yeah.
No one knows what the best platform is really to achieve this. It is true if you had a couple of hundred really high quality qubits, logical qubits that had good fidelity, and you could really run many operations. And you didn't need like a few thousand auxiliary qubits just to do error correction or something.
Yeah.
If you could do that, then you could do a lot of things. I mean, the big one that people talk about, of course, is factoring large numbers, which potentially could break a whole bunch of the encryption schemes that are used for things like banking online and for secure communications and for cryptocurrencies, these sorts of things.
And simulations, variety of simulations in life sciences as well as astrophysics, I think, right?
Yeah, I mean, there's a lot of there's a lot of effort going in on the part of very clever people thinking about algorithms where, how do you take the problem you're trying to solve and put it in a form where you can run it in some intelligent way on a quantum computer and really take advantage of the quantum advantage, the quantum computational advantage. And so there's certain there's a lot of interest in, again, this is almost going back to the chemistry stuff. There's a lot of interest in the understanding the properties of molecules, right? So if you could efficiently model the all of the properties of proteins in some very computationally efficient way, this would be a big deal, right? For drug discovery and things like that.
Right. Right. Yeah, in some sense, the condensed matter physics is sort of the engine of the train. If you don't make that engine work, many of the compartments, we cannot go any further than we have.
Yeah, I think there's some real truth to that, and I think the one aspect of condensed matter is that it has led to some realizations in recent years that maybe there are organizing principles that we weren't really thinking about before that we need to be aware of. Yeah. So an example of this, there's been a lot of work in the last 10, 15 years on topology, the importance of topology. So a lot of people have kind of a hand wave notion of what topology is. It's saying that basically, it's kind of the connectedness of things. It's the branch of math that tells you that a donut is different than a sphere, because a donut, is a surface of genus 1 and a sphere is a surface of genus 0, and that the idea that a donut can be continuously transformed into the shape of a coffee mug because you've preserved the number of holes, right? These kinds of ideas have really come to the fore in condensed matter in the last 10 or 15 years. And again, there's a lot of interest in, first of all, there's just the scientific insight that, boy, we really haven't been thinking about some of these things the right way. But then there's the possibility that these systems with interesting kind of hidden topological properties might really be useful for things. There's ideas about quantum computing involving topological qubits. There's ideas about materials where along the edges of these materials, you could imagine having charge flow with very, very, very minimal dissipation, because the scattering that usually gives you things like ordinary electrical resistance is sort of forbidden because of topological reasons. So, it's very interesting stuff.
Yeah, I don't know much about this, Doug, but so when we think about materials, don't we typically think about topology or geometry?
We certainly think about geometry in the sense of the spatial arrangement of the atoms.
Yeah.
I think the topology stuff that comes about is, and this is one reason why it's challenging to explain certain aspects of condensed matter to a general audience.
Yeah.
The topology that comes up in these systems really has to do with basically the properties of the electronic wave functions, like the quantum mechanical states of the electrons. And that's not something you can see with your eye, right? I mean, condensed matter, we're used to this idea that, like, look, I can tell the difference between a solid and a liquid. And I can tell, those are distinct states or distinct phases. And with very crude tools, I can tell whether something is a solid or a liquid. And then with more sophisticated tools, I can tell you what kind of solid it is. I can tell you how the atoms are arranged, right? Is it a cubic structure? Is it a hexagonal structure? Is it sort of more of a 3D network, or is it like a stacked bunch of two-dimensional layers? And we've gotten better and better at being able to characterize these things. The electronic, kind of the hidden away topology stuff, it's challenging to explain, certainly challenging to explain without pictures, because really it's not at all obvious to the naked eye. It's hard to point to some grossly clear physical property and say, aha, you see, that's how you can tell that this is, there's the hole in the donut. There's the thing that distinguishes these two things. One example of this is that, bismuth selenide is a topological insulator, it is called. I mean, it's also a semiconductor that's been very useful for thermoelectric applications. But, for something like 80 or 90 years, people had no idea that bismuth selenide was topologically interesting. And it was only in comparatively recent times that people realized, bismuth selenide has these weird properties. And what it really means is that the bulk of bismuth selenide acts like a semiconductor, but the surfaces have unusual properties. And we don't usually think about the surfaces. A lot of the math we learn when we deal with solids is really concerned with, here you are immersed in the bulk of some infinitely large material. But the topology stuff comes out at the surfaces and at the edges of things. And so that's one reason why it's been subtle for people to figure out.
Yeah, and it's also, Doug, would it be correct in assuming that some of these insights really come through experimentation, right? Not from theory.
So as an experimentalist, I should say absolutely yes. But I do think particularly on in the case of this topology stuff, I think theory has actually been extremely, extremely important. I mean, there's a healthy in condensed matter physics, partly because experiment is so accessible.
Right.
There is very often historically experiment has sort of taken the lead over theory, right? People have measured something weird, and then it's important to understand where it comes from. So, superconductivity was discovered in 1911, and it wasn't until 1957 that the theory of conventional superconductivity, the BCS theory, Bardeen-Cooper-Schrieffer theory, was formulated, right?
Yeah.
And so, that's the sort of the traditional order of events. But these days, theory has gotten more and more sophisticated, and there's been a healthy back and forth between theory and experiment. This is one of the challenges with high energy physics these days, which is that you could argue, theory that there had, with the exception of the discovery of the Higgs boson, which was in fact sort of expected for various reasons. There have not been any big experimental surprises in high energy physics.
Right.
And so the theory community has been a bit decoupled and has kind of gone off and pursued a whole lot of exotic things, hoping that there will be evidence for some of these things coming down the pipe. I mean, I don't want to sound like they're totally unmotivated. They've got good reasons for thinking about the things they're thinking about.
Yeah.
But there really is kind of a disconnect between theory and experiment at the high energy level in certain ways that is not true in condensed matter or in, atomic physics, where there's much more of a back and forth between theory and experiment, I think, these days.
Yeah, and the economics of the machines in high energy physics is sort of a limitation, right? And so as theory advances, and if you're requiring 10x, 100x energy levels.
Well, so that's really the question, right? So how much more energy do you need before you expect to see interesting, surprising things? If the answer is 3x, that's easily conceivable, right? If the answer is 30,000x,
Right.
then, and you'd need a particle accelerator the size of the moon, then, you start thinking to yourself, okay, there have to be different approaches to these problems that might be more practical to implement, right? And so this is in fact why there are all kinds of clever ideas out there now from the world of both condensed matter and atomic physics about, can we do precision measurements? Are there things we can do to infer about more exotic physics without necessarily having to build a, $500 billion giant particle collider?
Yeah, I remember reading, Doug. This was in Berkeley, I think. There's a group working there, sort of they call it a desktop collider or something like that.
Well, I know people at Stanford. I mean, there's a number of people who have thought about very compact ways of making particle accelerators.
Yeah.
I think wake field acceleration is a phrase that crops up, and I think there's progress being made. But the fact is that these days, the Large Hadron Collider is really where all the business is, at the energy frontier of particle physics.
Yeah.
The other extreme of this, of course, is astrophysics. I mean, there are astrophysical sources of very energetic particles, and so there are some beautiful experiments like IceCube down at the South Pole, where they're basically using the South Polar ice as a scintillator and detecting, cosmic rays and neutrinos from, highly energetic neutrinos from space by the flashes of light given off inside the polar ice.
Yeah. Excellent. So we will take a quick break, Doug. When we come back, we'll talk about some of your recent papers.
Sounds good.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we're back, Doug. We were talking about condensed matter physics, and sometimes because of all the exotic stuff that we hear in astrophysics and high energy physics, the public hasn't really attached to what condensed matter physics does. And it is a multidisciplinary field. There is a lot of material sciences type things involved there too. You have a few papers, recent papers, and one of them, electron pairing in the pseudogap state revealed by short noise in copper oxide junctions. You say in the quest to understand high temperature superconductivity in copper oxides, debate has been focused on the pseudogap, a partial energy gap that opens over portions of the Fermi surface in the noble state above the bulk critical temperature. Before we get into the details of this, Doug, I remember superconductivity again in the 80s. We were told that it is, just a few years away that we're going to get room temperature
Right.
superconductivity.
So
where are we now?
Okay, so here's the story. So superconductivity is this remarkable state that happens in some conductors. It tends to happen at low temperatures. And that it's what allows conductors to carry electricity, to carry electrical currents without any resistance. And certain very particular things have to happen in order for that to take place. We now understand. Yeah. One thing that has to happen, it would appear, is that the electrons have to pair up. So even though electrons repel each other, electrons pair up into what are called Cooper pairs.
Yeah.
And this is the Cooper of the Bardeen-Cooper-Schrieffer theory from 1957. And these Cooper pairs all decide to act cooperatively. So the one way you can picture it is, imagine you're having a dance, people pair up into partners, and pairing up is important, but the real superconductivity happens is when all the partners are all dancing together in sync. Okay. So go ahead.
Just a quick question.
Yeah.
So It has nothing to do with entanglement, though, right? This is something completely different.
Oh, well, that's a very complicated question. Certainly, entanglement is an important ingredient in this problem, because when you're pairing up the electrons, really you're entangling them with each other. Now, the kind of superconductivity that happens at really low temperatures that was discovered by Kamerlingh Onnes in the early 20th century, and happens in things like lead and niobium and aluminum. The glue that makes the pair stick together involves lattice vibrations or phonons, sound waves. Okay.
Yeah.
And so we kind of understand that pretty well. And there were good reasons to think that that mechanism was not going to work at temperatures above maybe 20 or 30 Kelvin, and at least under ordinary circumstances. There's a caveat to that I'll get to in a minute. So the big shock was in basically 1986. This class of ceramics was discovered. These copper oxides were found where they superconduct at say ambient pressures. They superconduct at temperatures as high as 150 Kelvin, which is basically halfway to room temperature, right? Room temperature is about 295, 300 Kelvin. So there was a huge jump basically in what people could do, and therefore there was an enormous amount of optimism that, oh my goodness, we're almost there. We can almost do this at room temperature. Well, of course, it turns out here we are, 35 years later, and we still don't really understand why the copper oxide superconductors behave the way they do. One of the avenues for trying to understand these materials. So I will say the quality of the materials, this is the materials science part, the quality of the material that people are studying has steadily gotten much better. And that way you really think you're looking at intrinsic things. You're not looking at, impurities or dirt that you're not controlling. But one avenue people have taken is trying to understand the normal state, the non-superconducting state. And the reasoning is, okay, in an ordinary metal like lead, we understand the metallic state of lead very well. It's what's called a Fermi liquid. We know what the low energy excitations of that are. They are these quasi-particles that act very, very much like electrons. They've got charge minus E, they've got spin a half. They live a long time, so to speak. So the assumption is if that's the starting ingredient for the BCS theory in the ordinary metals. And the thinking is it would be great if we could understand the normal state properties of the copper oxides. And that has proven really, really hard. So one of this particular experiment was designed with that in mind, was designed to try and look at the normal state of what's called one of the underdoped copper oxides. The native material, lanthanum copper oxide, is an insulator. It's a special kind of insulator called a Mott insulator. And if you do an atomic substitution and start putting in strontium instead of lanthanum, you make it more conductive. And at some point, there is an optimal amount of strontium you put in to get the superconductivity to have a maximal temperature. In that system, that maximal temperature is about 40 Kelvin. But it's a very well-controlled system on the scale of these things. And so the experiment we did, and I can talk about it in a second, is to try and understand the normal state. Now, my caveat from a minute ago, very recently, in the last 3-4 years, people have succeeded in getting superconductivity in very, very hydrogen-rich compounds, like lanthanum hydrogen 10, right? So 10 hydrogen atoms for every lanthanum atom, and also at crazy high pressures. So you make these very hydrogen-rich materials and you squeeze them literally between two diamonds to get up to very high, very, very high pressures. And it would appear those systems do superconduct, and they superconduct nearly at room temperature. Now, it's not super useful if you have to squeeze things, with thousands of atmospheres of pressure to make them superconduct. But what it tells you is that there's nothing, there's no roadblock in principle to having something superconduct at room temperature. The challenge is getting the right set of ingredients together.
Yeah, so the copper oxide So what happens, let's say, we get superconductivity at 100 Kelvin, for argument's sake.
Yep.
As you increase the temperature just above 100, it stops completely, or is there some kind of a variation?
So this is also an interesting question. So in a conventional superconductor, one of the old school kind, what happens is so lead, for example, the superconducting transition in lead is about 7.2 Kelvin. Below 7.2 Kelvin, the electrons like to pair up, and they form these Cooper pairs, and they form this condensate that acts as a superconductor. And then when you warm it up and you get to 7.2 Kelvin, the pairs fall apart, and the thing basically becomes a normal metal. And there's a very, very narrow region in temperature, maybe a small fraction of a degree, where it kind of looks like there's some superconducting fluctuations, maybe, but pretty much superconductivity is gone as soon as you really get above that transition. Now, in the copper oxides, one of the things we showed in our measurement, but we're not the only people who've shown this, other people with other indirect techniques have also shown this. The issue in the copper oxides, it doesn't seem like the pairs fall apart. They stop superconducting, but it's possible that there are still some pairs present above the superconducting transition, right? So that's different. That's different than the other case. And now, so it's to go back to my ballroom dance analogy.
Yeah.
It's not that you've lost it's not that everyone's lost their partners. It's just that each couple is no longer paying attention to what the other couples are doing. Right. And so here's the real attractive idea. If the pairing is really quite robust, then boy, wouldn't it be great if you could figure out how to reach in somehow and synchronize everybody up? Because if the pairing survives up to room temperature, then now you're talking about, well, we have a different problem now. Now it's not a question of forcing things to pair. It's a question of forcing things to be coherent. Right. And so that's kind of the interesting bit.
Yeah, I don't know anything about this stuff, but I was just thinking, if we cycle the temperature many times, would we see a difference?
In this system, not really. No. Okay. I mean, okay, if you cycle the temperature up to very high temperatures, it's high enough that atoms actually move around, then you've got problems. But I mean, if you just go back and forth across the transition, nothing history dependent happens.
Okay.
Basically.
Because the pairs remain, but they're not synchronized. So I guess the challenge is, could you take the structure and resynchronize it somehow, right?
Right. So there are people who are playing games with doing things with light, or otherwise, or otherwise trying to somehow couple into the pairs and get them to all dance together. Now, the experiment we did is basically, I can give you an analogy for that too. So we use what's called shot noise, which is the noise that results in the chart. So if you apply a voltage across some electrical object, right, and you have the current flow, you get some average current. And so we're used to the idea that this is how you define resistance, right? The resistance is the ratio between the voltage you apply and the current that you get. But you don't necessarily, you can get the same average current in different ways. And so you can have rain falling on your roof, and you could have the same rate of waterfall as a continuous fine mist or as a few widely spaced huge raindrops.
Yeah.
Right. So the current is the same, but the fluctuations are very, very different. And so by measuring the fluctuations in the electrical current, and comparing it with what's expected to happen if the electrons are just sort of randomly going through one at a time, you can figure out whether they're going through one at a time or whether they're sometimes going through as pairs. And so that's basically what we did. By looking at the fluctuations in the current and especially design structure, we could tell that even though we weren't in the superconducting state, that there were times when it sure looked like the electrons were going through two at a time.
Yeah. Do you have an intuition, Doug, as you look forward? So this appears promising, right? It seems like a somewhat of a different axis, that you have a structure remaining. do you think it is going to be a material science angle or something else to go further?
That's a really good question. I think certainly there are plenty of people who are interested in taking the materials approach of trying to understand. Particularly, there's like I said, there are people who are playing around with light as well,
Yeah.
to sort of use light to induce something that looks a lot like the superconducting state at higher temperatures. And I think what people are doing is they're looking at experiments like that and trying to figure out, okay, so you're turning some knob, you're perturbing the system in some way and stabilizing it at least temporarily in something that looks like a superconducting sort of regime. What would I need to do in terms of the material to get that all the time?
Yeah.
And the same thing is true with even these hydrogen-rich things. So the idea that like metallic hydrogen at high pressures could be a room temperature superconductor, that goes right. Yeah. But no one had ever gotten there, but I think now that people are getting close to at these high pressures with these hydrogen-rich materials, there are people who are looking at these and saying, okay, what would it take? What's happening at these high pressures? And how could I stabilize something like that with the natural structure of the material rather than having to squeeze on it with two diamonds?
Yeah. But the practical aspects of it, it seems to me that the copper oxide direction, but the pessimistic aspect of it, like you say, we are sort of standing still for 35 years.
I don't think that's a fair. Well, two things. First of all, I don't think that's a fair assessment. I mean, I think we've learned a lot. I do, and also I will say that there are actual applications of high temperature superconductors. I mean, there are magnets for various industrial applications based on high temperature superconductors. This group at MIT who wants to do a very compact fusion reactor, the whole trick there is they're using high temperature superconducting magnets that enables you to get much higher fields and therefore make a smaller device. So we have made progress. It just, the initial forecasts were very optimistic, right? And the other thing that people underestimated, and this tends to happen anytime you really want to make major industrial advances in a new material system, it always takes longer than you think. So I'll give you another example, right? People figured out in the early 90s how to make nanocrystals of some semiconductors, like 2,6 semiconductors, like cadmium selenide.
Yeah.
And these crystals have remarkable fluorescent properties, and they can be used for all kinds of different things. And it took 20 years before people solved not so much the science problem, but the chemical engineering problem of really making ton quantities of these things with reproducible properties. And now, of course, you can buy flat screen televisions that have these quantum dots in them, right? But it took 20 plus years. And so, the fact that it's taken 35 years doesn't so much shock me. I mean, I think people are very, very spoiled by things like silicon.
Yeah.
But even silicon, if you look at it, we're reaping the benefits of basically 75 years of intense research by thousands of people. So the reason silicon is as capable as it is because a remarkable amount of effort has been put into place into understanding silicon. This is why whenever I hear people say, "Oh, we're going to use two-dimensional semiconductors to replace silicon in 5 years," I'm like, no, you're not. I mean, it may happen eventually, but like the material quality, like the reason, the kind of silicon we can grow for semiconductor applications, it's pure to a part in a trillion, right? And they can grow single crystals as big as dinner plates in diameter. I mean, it's just astonishing what's been achieved.
Yeah.
And so anyone who thinks they're going to supplant that technology in a few years is just not realistic.
Yeah, I mean, the scale up is always an underappreciated problem because we think engineering problem, and engineering problems can always be solved, but often it takes time.
Yep.
So I want to finish up with your most recent paper, Thermoelectric Response from Grain Boundaries and Lattice Distortions in Crystalline Gold Devices. So this is something that you did with a group at Stanford?
Yes, yes. So this is a fun one. So thermoelectricity is this phenomenon where if you take a conductor and you make one end hot and one end cold, you will build up a voltage across the conductor. And this was identified by a fellow named Seebeck, 150 years ago or more, maybe even longer than that. I have the feeling it's almost 200 years, actually. And it's the basis for basically the thermostat in your house, probably, right? Or the thermocouples that measure the temperature inside your car. You take a couple of different metals, you stick them together, and if you keep the far ends of these things at a fixed temperature and the junction between them at a different temperature, you generate a voltage, and you can use that for thermometry. So usually you think that if I have a single material, its properties just are what they are. And so if I heat, if I inhomogeneously heat this material, so imagine I've got like an iron bar and I heat the middle of it and I measure the voltage between the two ends, I should get zero because it's all iron. So the thermoelectric properties of iron are uniform as I go along the iron bar. And so, in the end, I get nothing, right? But it was found a few years ago that, and in hindsight, it's not that surprising, that's not really true, in the sense that if you make things sufficiently small, so the thermoelectric properties result from how the electrons scatter, and and you can change how the electrons scatter off of disorder and off of various things by making your system small. So if a dominant part of the scattering is like bouncing off the walls, then by changing the geometry of your device, you can make, you can basically have a fat wire attached to a skinny wire, even if it's all the same material. If the fat wire is 500 nanometers wide and the skinny wire is 100 nanometers wide, it'll act like a thermocouple, and you'll get interesting thermoelectric physics. And so what we had found was that we were very surprised to find that you can make what you think of as a thin film of metal, in this case gold. It's made up of a bunch of little crystals. And we were surprised to find that what we thought was a uniform film, and like electrically it looks like a very nice uniform film, had all kinds of weird local variations in its thermoelectric properties, and we didn't understand that. And so we worked with this group at Stanford. We assumed when we were starting out on this that, well, okay, the issue has to be the grains. It has to be that the grains and the way the different crystal grains fit together, that's the problem. That's the issue. Yeah. And so this group at Stanford, led by Jonathan Fan in electrical engineering there, they had come up with a technique for growing single crystal gold wires. And even cooler than that, they could grow a wire that was made of exactly two crystals and one boundary between them. And we thought, oh, this is perfect. This is a perfect system. We can look and see whether one single grain boundary does something interesting, right? And so the way we do the experiment is we use a laser as a scannable heat source, basically. And we have a laser and a voltmeter, and we scan the laser over the system and measure the voltage across the system. And what surprised us was the grain boundary itself doesn't really do much of anything. What does matter is these crystals aren't perfect, and very subtle structural defects with the crystals totally matter. So it turns out that strain matters, right? If you've got strain and plastic deformation and any kind of dislocations and kind of any structural imperfections, it affects the thermoelectric properties enough that you can measure it. And that was surprising to us. So that's what that paper was. We actually have a paper that we're getting ready to submit now that's related, where it turns out you can also use the same measurement technique to identify tiny amounts of impurities in your material as well.
It sort of sort of the history of the crystal, right? I mean, if you think about structural defects and strain.
Oh, absolutely. So one way we persuaded ourselves that what we were seeing was really partly a strain effect.
Yeah.
Was you take devices and you anneal them, right? You treat them you treat them differently. You hold them at elevated temperatures for longer, so that you like to think that certain kinds of structural defects will sort of heal themselves, and you see what happens in the response. And so that was one way we decided we that was one piece of collateral evidence that these structural defects and strain were important here. But yeah, it all comes down to how you treat the stuff. So I mean, so the bottom line is, if you want to, the wiring in your computer chips, for example, it's strained, right? I mean, it's copper in very confined geometries. It's put down in a very particular way. It's thermally cycled in certain ways, and it probably has baked into it, certain kinds of structural imperfections that you could probably go and look for with this technique if you wanted to.
Do you see any sort of direct applications here? Can you sort of design in a strain to get some properties?
That's an interesting question. So that's something that we've thought about. I think what I think would be interesting would be to do the experiment to directly measure the effect of strain at this level. You could do it. It would be, so there are people who are very good at making micro machined actuators and things, the same sort of stuff that basically is like the accelerometer in your phone that tells it which way to orient the screen, or the airbag sensor in your car. These micro machined platforms, you can make those in a way where you could basically, if you worked hard enough at it, you could take one of these wires and you could pull on it and know exactly what kind of strain you're doing and see what the effect is. I think that, I mean, it would be sort of a heroic experiment, but it might be very interesting to do. And that, I think there are opportunities. I think it's just engineering, really engineering the strain in some of these systems is hard.
Yeah. Excellent. So in conclusion, Doug, what would you like to say to prospective students of condensed matter physics looking forward 5-10 years?
I think this is one of the most exciting areas of physics. There's a lot of action going on. And I should also point out, condensed matter touches, apart from the profound aspects about, topology and emergent properties, and what does it really, what do we really mean by fundamental? You get all sorts of exotic physics like charge fractionalization and spin liquids and highly entangled systems. Apart from that, condensed matter, has a role to play in many, many future technologies, including the world of quantum information. And I want people to appreciate, the remarkable physics at work in the world around them every day. And I think, it's an example of a field of physics that is thriving and very active. And I think sometimes in the popular press, people will write articles. John Horgan will write an article in Scientific American about the end of physics. And, these kinds of things just annoy me because basically it's basically saying high energy particle physics equals all of physics. And that's just not accurate. And it also sort of implies that, but high energy particle physics is really the fundamental stuff. Like, I don't think that's obvious. I don't think it's obvious that the only way you can get fundamental insights is from kind of the reductionist high energy paradigm. I think there's a lot of fundamental insight to be gained by looking at emergent phenomena. So come on in and join the party. It's fun.
Excellent. Yeah, this has been great, Doug. Thanks so much for spending time with me.
My pleasure.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.